All right, everyone. So last time we talked about the circumcenter and perpendicular bisectors and how those are related to each other. Today, we're talking about angle bisectors and incenters and how those are related to one another and some different theorems that we can use to solve for missing things. So let's get started. First off, we have to remember that an angle bisector is a ray or a line that divides an angle into two congruent angles. All right, so that was from chapter 1, a line or array that divides an angle into two congruent angles. So today we're going in the direction of the angle bisector theorem, which is that if a point is on the bisector of an angle, then it is equidistant from the sides of the angle. So we're going to draw a picture of what that looks like here. So starting with an angle. Let's call it angle A. And then we've got the angle bisector. And we know it's an angle bisector because it's showing that these two smaller angles are the same length or the same size. And then we're saying if there's a point out here on that angle bisector, then we're going to draw that same picture and add some stuff to it. All right, so if that's the case, then that point P is the same distance from P to one side of the angle as it is from P to the other side of the angle. That's the same distance on both sides, which should kind of make sense in our heads because if this is cutting the angle in half, it should be the same on both sides, right? That's what half is. So that's what we know from the angle bisector theorem. The other way around, of course, the converse of the angle bisector theorem is that if a point in the interior of an angle is equidistant from the sides of the angle, then it is on the bisector of the angle. So this is another thing we can use to kind of help us identify an angle bisector. So we're going to start with the same kind of drawing. We're drawing an angle. But this time, I'm going to put point P somewhere out here in my angle. And I'm showing that P is the same distance from both sides of the angle. So if we have that, then same thing, adding stuff to it. All right, so P is equidistant from both sides of the angle. Then the angle bisector is going to go through that point P. So if I've got a ray that goes through point P, I know that that ray is an angle bisector. So that can help me to identify an angle bisector if I did not have the markings of an angle bisector on there. Okay. Then we're going to take a look at some examples of what this allows us to do. So looking down at this one, we want to know what is EH. All right, so EH is this one. We might notice in the picture that these markings are here showing us that this is an angle bisector. So if this is an angle bisector, then this point H must be equidistant from both sides of the angle. And so since this is 23, this distance would also be 23. So EH would be 23. All right, so that's one thing we can do with the angle bisector theorem. Now we're going to use the converse of the angle bisector theorem. So on this one, we're looking for the measure of angle QRS. So that would be this angle right here, this whole thing, QRS. And we should notice that this 7.5 is the same distance as this one, also 7.5. So that should tell me then that this is an angle bisector. So if this is 26, which I know it's kind of fuzzy, but it's supposed to be a 26. So if that's 26, then this is also 26. So the whole thing, 26 times 2, which is 52. So 52 degrees for angle QRS. Okay. So those are kind of the simpler versions of this. Now we're going to stick some algebra in there. Also, this is supposed to say 2x plus 5. This is supposed to say 4x minus 25. I know it doesn't look like it. All right, so on this one, we should notice that these two are marked as being the same distance, making this an angle bisector. So if that's an angle bisector, then we can set those two things equal to each other and solve for x. So 2x plus 5 equals 4x minus 25. Then we subtract 2x from both sides. And then we add 25 to both sides. And then we divide by 2 on both sides to get 15 equals x. And that's our answer because on this one, all we were asked to find was x. All right. So those are the things we need to be able to do with the angle bisector theorem and the converse of the angle bisector theorem. The next thing we need to talk about is something called the incenter. So just like the perpendicular bisectors and the circumcenter were related last time, where the circumcenter was the intersection point of all of the perpendicular bisectors, this incenter is the intersection point of all the angle bisectors. So there's a couple ways that we can know that it's the incenter. The first way is if it tells you that in the problem, then obviously it's the incenter. Another way you can know is if it points out that these three things are angle bisectors. Then we would know that that's the incenter. And the third way is just by the markings in the picture. If you can tell that these are marked as being congruent angles, these are marked as being congruent angles, and these are marked as being congruent angles, that tells you that these are all angle bisectors, and therefore this would be the incenter. So there's a couple ways you can tell what it is, and there's an incenter theorem that goes with it, which says the incenter of a triangle is equidistant from the sides of the triangle. So over here, if these are all angle bisectors, that means that AC, AB, and AD, all three of these distances are the same. And the interesting thing with this is kind of like yesterday we did with the circumcenter. You know, we had that center be the center of the circle, and then we drew a circle around it, and each of the vertices of the triangle were on that circle. The incenter, if I make a circle that has a center at the incenter, I can make a circle that touches the sides of the triangle in these places all just once. All right. So that's another cool thing with the incenter. Now let's go ahead and turn the page and see what kind of problems we're going to be asked to do with this. All right, so the first one is simple. The angle bisectors of a triangle intersect at point P. That tells me that this is the incenter. Before I do anything, I'm going to label what things will be congruent, and it's going to be these three distances. So that means that since this one is 8, these two are also 8. And since we're asked for PS, which is this one, we can say that PS is 8. Cool. Same kind of thing happens for number 5. So pause the video real quick and do number 5 on your own, and then we'll check it. All right, hopefully you paused it and did number 5. On number 5, N is the incenter. So all of these are the same. So NF will also be 2, since these all three will be 2. All right, number 6, we step it up a little bit again with adding some algebra to the mix. But still, P is the incenter, so all three of these will be the same. We are told what PJ and PL are. What I need to do with those is then set them equal to each other. 4x minus 8 equals x plus 7, and solve for x. So minus x on both sides, plus 8 on both sides. Divide by 3 on both sides. We should get that x equals 5. So there's part of my answer. And then I'm asked what pk is. And pk is this other one, but it's going to be equal to these two. So since I know that pl is x plus 7, I can go, okay, well then that's 5 plus 7, since x was 5, which is 12. So that means that each of these will all be 12. All right. Number 7 goes pretty much the same way. So go ahead again and pause the video, try number 7 on your own, and then come back and check it with us. All right, so hopefully you did that. We're going to show number 7 real quick. GM, GN, and LG are all the same because G is the incenter. So 6x minus 14 equals negative 3x plus 22. Add 3x to both sides. We get 9x over here. Add 14 to both sides. We get 36 over here. Divide by 9 on both sides. We get x is 4. All right. Then you go plug it back in just like we did with the others. Negative 3 times 4 plus 22, which is negative 12 plus 22, which is 10. So all three of these will be 10. Okay. So last thing we want to do today is kind of look at the difference between the incenter and the circumcenter, because now that we have two different centers, we need to be able to tell them apart. So we're going to kind of summarize that real quick. I'm going to make a quick chart with circumcenter on one side and incenter on the other. All right, so the first difference is that the circumcenter is the same distance from the vertices or corners of your triangle, whereas the incenter is the same distance from the sides of your triangle. All right, so that's one way we can tell them apart, and that's probably the most important thing we need to know about each of them. The other important thing we need to know is that the circumcenter is made by the perpendicular bisectors. Particularly, it's made by that spot where they all intersect. Then the incenter, though, is made by the angle bisectors. And the place that they all intersect. So those are the main things we need to know about the circumcenter and the incenter. All right, that's all I got for today. If you have any questions, let me know. Otherwise, have a good one.